Hello there, and welcome to this collection of notebooks and tutorials on multi-rate signal processing. This is a course offered by Professor Schuller at the UMNL University of Technology to different master's degree programs. I am Renato, the instructor for these online materials, and on this notebook we'll talk about transforms as filter banks, specifically the discrete Fourier transform, the DFT, as a filter bank. Let's get started. From the definitions of previous lectures, we know that the DFT of a block signal X is defined as this sum here. Therefore, we can rewrite the DFT as a matrix multiplication with the matrix T with the elements given by e to the power of minus j 2 times pi divided by capital N times k times n, where n is the time and row index, and k is the frequency and column index. Using the signal block vector given here, we can rewrite the DFT of block M as a matrix multiplication. Y of M is equal to X of M times T, where T is a matrix with these elements here. This is the matrix formulation of the DFT, where the matrix multiplication given here is Yk of M, is this sum here, like we've seen, similar to this here. Here now we can extract the equivalent impulse responses. Now we can compare the above transform on 3 with the convolution and the downsampling equation given here. So we have this symbol here to indicate that there is this downsampling, and we see that here the index n for our signal X has the reverse order or reverse sign as in equation 3. But since we're interested in the equivalent impulse response, we simply reverse the index order in the transform equation 3, and we can use index substitution when n is substituted by n minus 1 minus n prime. So this is what we will do. We will substitute n by this here, and we will still obtain the sum because the sum ordering doesn't change the result. So now we have here this equation with the sum, and we replaced n by n minus 1 n prime, and we get this equation here. When we compare this with our convolution sum in equation 4, in here, it looks like the convolution sum with the phase index of n0 equals to n minus 1, and with filter length equal to the block length L. So L equals to n when we compare these two equations here. This indicates that Yk of M contains phase n minus 1 of the downsampled subband signal. Through this comparison, we obtain the equivalent impulse response of our DFT given by here. So this is the equivalent impulse response. This is now the equivalent analysis impulse response of our DFT, interpreted as an analysis filter bank. Observe that it can also be interpreted as a rectangular window of length n with modulation of this exponential term. In conclusion, the DFT can also be seen as a special kind of a filter bank. Each DFT coefficient can be seen as a sample of one of the downsampled subbands. Each column of our transform matrix T represents the impulse response of one subband filter, but in reversed order. We can read the impulse response out of the transform matrix starting from the bottom and going up. We still need to find the equivalent synthesis filters if we apply the inverse transform for the perfect reconstruction of our signal. We get perfect reconstruction, the original signal, if the transform T is invertible. For mathematical formulation of the inverse transform, we can again write the reconstructed signal X hat as a sequence of blocks, like we did before. We can obtain the reconstructed signal by simply multiplying the blocks of subband samples Y of M with the inverse transform matrix, so given here. The elements of this inverse DFT matrix are given by these equation here. Now equation 5 can also be written as this here using rows times columns. So we have the sum, okay, going from 0 to n minus 1, n is 0 to n minus 1. That's equation 6. To see the resulting impulse response of the equivalent synthesis filter bank, we need the equations for upsampling and filter in the synthesis filter bank. In the synthesis filter bank, the subband's signals yk of m are upsampled first, and we obtain the upsampled signal with phase 0 and time index n because we are at the higher sampling rate. The following filtering is the convolution with the synthesis subband impulse responses gk of n, hence we get the output of the kth filter as given by equation 7, where L is the length of the synthesis filter. We assume that L is a multiple of n, which we can always obtain by appending zeros if necessary. Observe that most of the samples of y upsampled n are 0. To rewrite this equation here such that we only process the non-zero samples, we again use the blockwise processing by substituting n by m times capital N plus n and n prime by m prime times capital N plus n prime, using block indices m and m prime, and in block or phase indices n and n prime to obtain this double sum here. Here we can see that we get the non-zero elements of y upsampled of n if its argument is integer multiples of n, and we get this if we have n equals to n prime. Because of this, the inner sum only consists of one summand, because the sum over n prime disappears. So when we make n equals to n prime, we will have here the inner sum consists of one summand, and the sum over n prime disappears. So we end up in this case here. For the reconstructed signal, we simply add up all the n subbands. So now we're adding up the n subbands. From here we add up all the n subbands, and here we can now replace the y upsampled k m times n by yk of m, since we now address only the non-zero elements. And we reach here equation 8. This is now our reconstructed signal, where the first sum is over the subbands and the second sum is over the blocks. At this point, we can compare this filter bank equation 8 with the synthesis transform of equation 6. And we have here equation 6. We're just repeating it here, and we can compare with equation 8. First, we see that the transform of equation 6 has no sum over the blocks, meaning the filters only have length L equals to n, hence the inner sum disappears with m prime equals to 0. With this, equation 8 becomes this equation here. And when we compare this with the transform equation 6, we can see now the equivalent impulse response are given by jk of n, given by this here. Looking at our transform matrix, we see that these impulse responses correspond to each row of the inverse transform matrix, non-reversed. In conclusion, the impulse responses of our subbands are the rows of the synthesis transform matrix, here not time reversed. We can read out the impulse responses of the synthesis filter bank from left to right in each column of the transform matrix. Observe, each time we got our result by comparing the convolution sum of our equivalent filter bank with the transform sum. This theory can seem a little bit complicated, so let's take a look into a Python example so we can try to clear some points out. So take a DFT of size n equals to 4. Its transform matrix T can be obtained using this FFT, FFTI. So we have our transform matrix here. Observe that we have complex values in the transform, and hence we obtain complex valued filters. To evaluate complex valued filters, we need the full circle in the frequency domain from 0 to 2 pi. If we want to obtain the frequency response of the subband k equals to 1 of this DFT filter bank, we take the second column, time reverse it, and then plot the frequency response with SciPy signal frac z. So here we are importing a SciPy signal, matplotlib to plot numpy, and here we are computing the frac z, so the frequency response of subband k equals to 1. Here is just to avoid log 10 of 0. And now we're plotting the magnitude response for the TFT for subband k equals to 1. So we have dB and we have normalized frequency. Here is approximately pi, and here we are at 2 pi. Observe we have a bad stop band attenuation, so it's less than 20 dB. Also observe that the frequency axis is going from 0 to 2 pi instead of just pi. This is because we have complex impulse response. The normalized frequency 2 pi is the sampling frequency. Since we have a 2 pi periodic frequency, this is identical to frequency 0, and the frequencies from pi to 2 pi can also be seen as the negative frequencies from minus pi to 0. This shows that this filter has a pass band at the positive frequencies, but not at the negative frequencies. The equivalent pass band at the negative frequencies is obtained from subband k equals to 3. So first we plotted the subband k equals to 1, now we move to subband k equals to 3. We do the same procedure, we calculate the frequency response, and we have the magnitude response for the DFT subband k is equal to 3. Observe that this looks like the frequency mirrored version of the filter for k equals to 1. This also shows how to separate positive and negative frequencies. The low pass is at k equals to 0, and the high pass appears at k equals to 2. Observe that here the high pass appears in the middle because of this symmetry between positive and negative frequencies. In this example now we show that the transform is indeed a special case of a critically sampled filter bank with the above computed filters. So let's take an example signal of length equals to 8. So here what we're doing, we are having here a signal length equals to 8. We have this array here, and then we do its decomposition into blocks of length 4 by using this convenient Python NumPy indexing here. So we have here decomposition into blocks of length 4. Again, we obtain our DFT transform matrix using the FFT and I that we have here, and we obtain the transformed blocks with this dot multiplication of our decomposition into blocks of length 4 and our transform matrix. And this is the result y of t. Here, each row contains the spectrum of each corresponding block. Now, we process the input signal x through a critically sampled filter bank with the equivalent filter impulse response. The transform matrix columns flipped up down and downsampled with the last phase of the blocks, and 0 equals to capital N minus 1, which is equal to 3, as it appeared in our derivation of the equivalent impulse responses. So here we have this filtering, so we're flipping, and here we get the output of this filtered signal through a critically sampled filter bank. Now let's compare with y of t. So y of t was given here, and now y is given here. And we see that y of t from the transform and y from the critically sampled filter bank are indeed the same. So we do did two different procedures. Here we did a matrix multiplication, and here we did filtering. So using the critically sampled filter bank with the equivalent filter impulse response, but we achieved the same results. In conclusion, we see that a transform is a special case of a filter bank. The tool of reading out the impulse responses from a transform matrix allows us to analyze the resulting filters and to judge if they fulfill our requirements.